AP Chemistry. We're on to a new unit, the second to last unit in this class. It's called Thermodynamics. It's an extension of a unit we did earlier in the semester called Thermochemistry. And the first lesson here is on a topic called Gibbs free energy. So, what is thermodynamics? Thermodynamics is the study of energy into or out of a physical or chemical process. So physical and chemical processes want to move to lower energy. So take the following chemical reaction and its reverse. So 2H2 plus O2 produces 2H2O. We've seen that reaction before for water. Then the reverse of that would be 2H2O would dissociate and become 2H2 plus 2O2 plus O2. So which of these reactions happens naturally? There's one of them that under certain circumstances, temperatures, pressures will naturally happen. The other one won't happen. So the one that will actually occur is the one that takes the reaction to the lowest energy state. But which one is that, and what kind of energy are we talking about? So we've already dealt with the energy in the form of enthalpy delta H, and that's heat energy going into or out of a chemical reaction. So here, for example, we have the combustion reaction of methane. So you put methane with oxygen, you light a match, and it burns and it produces carbon dioxide and water. And what it also produces is heat coming out. We know that that's going to create warmth, heat. So the delta H of that reaction is negative 890 kilojoules per mole of heat, or enthalpy, will come out of the reaction when you burn methane. So an exothermic reaction occurs when heat comes out of a reaction and it has a negative sign. So again, the metaphor was, the analogy was, think of it as money out of your bank account. An endothermic reaction occurs when heat goes into the reaction and it has a positive sign. So that's money going into your bank account. So the only kind of energy we've ever talked about in this class is the heat energy going into and out of a chemical reaction, and we call that enthalpy. So there are two basic rules of physics that describe how chemistry works. And they are physics principles, but they describe how chemistry works. The first one is that negative attracts positive and negative repels negative. We call those Coulombic forces. And just about everything we've talked about in this class has to do with that. Something that's negative, something that's positive, whether they attract or repel each other. The second one is that chemical processes naturally move from higher to lower energy. But we have also experienced this, that some reactions are endothermic, which means that the reaction takes in energy and ends up at a higher energy than it started. So how can that happen? If chemical reactions naturally want to go from higher to lower energy, they should all be exothermic. And at one time in the history of chemistry, chemists thought that, yeah, all reactions are going to be exothermic. They have to give off heat energy. But we know that's not true. We know that there are reactions that take in heat energy during the reaction and end up at a higher energy level than they started. So this seems to violate rule number 2 up there, that chemical processes naturally move from a higher to a lower energy. So far, the only kind of energy we've talked about is enthalpy, and that's delta H. But if chemical systems must move from higher to lower energy, there must be another kind of energy that we're talking about. Because clearly sometimes enthalpy is positive and heat energy goes into a reaction. So if rule number 2 up above is going to be true, there must be a different kind of energy that we're talking about. So this lesson deals with this new kind of energy called Gibbs free energy. By computing the Gibbs free energy, also called free energy, of the reaction, we can determine which way the reaction will run naturally. Free energy is abbreviated with the letter capital G. So 1, if the change in free energy is negative, delta G is less than 0, then the reaction will naturally flow in the forward direction from left to right. If the change in free energy is positive, delta G is greater than 0, then the reaction will naturally flow in the reverse direction. And if the free energy is equal to 0, delta G equals 0, then the reaction is at equilibrium, and the reaction will just stay right there in its current position. Okay, in this unit, you will learn to compute free energy from the standard free energy, which is G with a little circle up above. That just means the free energy that will occur at certain temperature conditions. Also from the reaction quotient Q. We studied about that in the equilibrium unit. Q was a number that you get by plugging in the current concentrations of the products and reactants into the law of mass action for equilibrium. And if the Q was less than the equilibrium value K, then the reaction would move forward. If Q was greater than the equilibrium value K, then it would move backwards. It would move in the reverse direction. By the end of this unit, you will be able to determine which way a reaction will run naturally based on external variables such as temperature and the reaction quotient. So what is thermodynamics? Thermodynamics is the study of free energy into or out of a physical or chemical process. The process can be a chemical reaction such as 2H2 plus O2 produces H2O. Or it could be a physical reaction such as the melting of ice into liquid water. So H2O solid to H2O liquid, that would be ice melting. In this unit, we will use 3 laws of thermodynamics. The first law of thermodynamics is energy is neither created nor destroyed. It simply can change forms. The second law of thermodynamics is that entropy, to be defined later, of the universe increases in a spontaneous process. And the third law of thermodynamics is that the entropy of a perfect crystalline substance at 0 degree Kelvin, which is the lowest temperature in the universe, is S equals 0. S is the abbreviation for entropy, and again, we'll get into that definition in just a moment. A spontaneous process is one that happens naturally with no outside influence. So when SpongeBob drops his pencil, it is a spontaneous process because the pencil falls naturally to the ground. When SpongeBob picks up his pencil, it is a non-spontaneous process because it requires energy to pick the pencil back up from the ground. So both cannot be spontaneous. If the one on the left is spontaneous, then the one on the right cannot be spontaneous. It doesn't happen naturally that a pencil just flies up from the floor into your hand. So that's not spontaneous. So the word naturally was used earlier. It meant spontaneously. A spontaneous process is one that happens naturally with no outside influence. So a car will spontaneously rust in natural environmental conditions, but to restore a rusty car would be a non-spontaneous process because it would require an input of energy. Entropy is an increase in the disorder in the universe for any spontaneous process. So you have to keep that definition straight in your head. Increasing entropy means you're increasing disorder, not order. So entropy means disorder. Increase in entropy is an increase in disorder. A decrease in entropy is an increase in order. And it means something's becoming more orderly if you decrease the entropy. So keep that straight. It's easy to get it backwards at first. Okay, so a broken wine glass has a greater entropy disorder than a wine glass that is not broken. It's just very simply that. The molecules in the glass are in a more disorderly state when the glass is broken than the molecules in the glass, which is more orderly. The symbol for entropy is capital S. The units of measure for entropy is joules per Kelvin. So it's an amount of energy in joules over the absolute temperature scale in Kelvin. So just remember, entropy equals disorder. So the units of joules per Kelvin can be understood with an example. If heat measured in joules is released into a hot room, that is, it has a high K, a high temperature, it hardly changes the motion of the molecules. So this means there's a small change in entropy. The ratio of heat to Kelvin is low. That would be a small change in entropy. You would not feel any of the heat in an already hot room. The small increase in the speed of the molecules is a small delta S, that is change in the heat energy of the molecules over the temperature. So you would hardly see any change in entropy. So example, you're sitting in a room that is 310 Kelvin. That's really hot. That's about 100 degrees Fahrenheit. Okay, so the unit of joules per Kelvin can be understood with an example. So if heat measured in joules is released into a cold room, a low temperature in Kelvin, it changes the motion of the molecules more greatly, because initially they were moving very slowly, they had very low energy. Now you've put that same amount of heat into that room, that's going to cause them to speed up quite a bit from what they were doing before. So this means there's a large change in entropy when the ratio of joules to Kelvin is high. So you will feel the heat coming out of that heater in a cold room. You wouldn't feel the heat coming out of the heater in a hot room, a room that's already hot, but you're going to feel it in a cold room. You'll definitely feel the heat coming out of the heater. So the large increase in the speed of the molecules is a large delta S. That's change in entropy. So there we see that again. The units are joules per Kelvin. So let's take an example. Let's say 50 joules of heat are released in a 310 Kelvin room. That's about 100 degrees Fahrenheit. What is the change in entropy? So we simply do that division problem. We get 0.16 joule per Kelvin. If the same 50 joules of heat are released in a cold room, that's 32 degrees Fahrenheit. That's the freezing point of water, 0 degrees centigrade. What is the change in entropy? Now the 50 is divided by 273, and you get a little bit larger number for entropy, 0.18. Now, really just intuitively understanding what the 0.16 and 0.18 is not really important. It's just important to understand that you caused a greater change in the disorder of the molecules. When the molecules move faster, they're more disorderly. You caused that was greater when you did it in a cold room, when the heat relative to the temperature was greater than in the hot room, where the change in heat relative to the temperature was less. So that's all you really need to understand. So the heat has a greater effect on the entropy of the cold room, and you would feel the change in entropy more in the cold room. Entropy is an increase in disorder for any spontaneous process. So dissolving an ionic compound such as KBr, could be anything, could be table salt, is a process that is both spontaneous and increases entropy because the ions are in a greater state of disorder. So you see on the left, when they're dry, the KBr is a nice crystalline structure. That's a crystal lattice structure. And just like table salt, when you put it in water, those ions are going to break apart. So they're more orderly on the left, they're less orderly on the right. So dissolving a substance is considered an increase in entropy. In chemistry, entropy is the number of possible ways that atoms or molecules can be arranged. More possible arrangements means more disorder and therefore more entropy. So in ice, the H2O molecules are arranged in a specific order. This is a low entropy. It's very orderly. Water, in liquid water, the H2O molecules have more freedom to move around. This is greater entropy than ice. And in steam or vapor, the H2O molecules are completely free to move around. This is the greatest entropy. So I think the concept's pretty simple. It's just how free they are to move will determine how much entropy they have, how disorderly they are. A spontaneous process must be 1. Irreversible. 2. Increase the entropy of the universe. We're going to see what that means in a little bit. So rule 1 means that the reaction cannot be spontaneous in both directions. If it is spontaneous, happens naturally in one direction, it cannot spontaneously happen in the other direction. So the SpongeBob example, a pencil cannot spontaneously fall from your hand to the ground and also just spontaneously naturally fly from the ground back up to your hand. It's one or the other. It can't be both. Rule 2 means that you can decrease entropy disorder in a system, but the entropy of the universe must increase. So think about this example. Let's think about the literal universe, and let's think about the system as being the Earth. So when life on Earth formed, this was a great increase in order, which means a decrease in entropy. In other words, going from nothing on Earth to living organisms is a great increase in order. So that's a decrease in entropy on Earth. However, the entropy of the entire universe had to increase by a greater amount than the decrease of entropy on the Earth. So you can decrease the entropy, the disorder, at a very specific location in the universe, but overall the whole universe is going to experience greater entropy. It's going to have to give up more energy to create that order in that very specific location. So overall, the disorder of the universe, total disorder of the universe, the total entropy of the universe is going to be greater. So example. So Mr. Mellinger's class is behaving badly. The class has high entropy disorder. So he asked Mr. Babineau to send other teachers to help manage the class. So there they are. There's all the other teachers, okay? And so I say, help. I need help managing my class. So all the other teachers in the school come over to help me manage my class. So Mr. Mellinger's class is now more orderly. The entropy has decreased. However, with all the other classes unattended by teachers, the overall entropy of Hoover has increased. So even though they've decreased the entropy in a very specific location, my classroom, the overall entropy on the disorder and the rest of the campus increased. And not only did it increased by a greater amount than the reduction in disorder in my classroom. So if you look at Hoover overall, my classroom and the rest of the campus put together, overall the entropy increased. The campus became more disorderly, even though my room became more orderly. So this means that we can decrease the entropy of a specific system, that's a location, but the entropy of the universe overall will increase. That is not only the rest of Hoover, but my classroom as well. If you took the total entropy of the two of them together, the entire campus, including my classroom, the entropy would have increased overall. Okay, factors which affect standard entropy are: 1. The states of matter. Gases have greater entropy than liquids, and liquids greater entropy than solids. That goes back to the ice example. Ice has more order in its molecules than does gas. So gas would have a greater entropy. The molecules can move around more freely, more disorderly. Molar mass. So entropy increases with the molar mass. That is, larger molecules are they move in different ways. They have more different ways that they can move around, that they can vibrate, that they can move. And so molar mass, the larger the molecule, the greater the entropy. Allotropes. Different allotropes have different entropies. Allotropes are two different forms of the same element in structures. So graphite, which is a very soft form of pure carbon, and diamond, which is a very hard form of pure carbon, are both allotropes of carbon. Dissociation. When an ionic compound dissolves in water, it will have greater entropy than the solid by itself. So when you dissolve salt in water, you get sodium and chloride ions, and so that's greater entropy. They float around freely in the solution. They're not the nice crystalline structure like we saw back on an earlier slide with KBr. So that would be greater entropy when they dissociate, when they dissolve. And molecular complexity. An increase in the complexity of a molecule increases entropy. That's because there are more different arrangements that the atoms can have. It also means that they can wiggle and vibrate in different ways. So more complex atoms, those with more different elements, they have different electronegativities. There's just a lot more differences to create more disorder or more different possible states that they can exist in when they're more complex molecules. So molecules can have three kinds of motion. Translational motion, this is the motion of a molecule moving from one place to another. So this is an example right here. It moves from there to there. That's a translational motion. Vibrational motion, this is the motion of the atoms in a molecule moving around, and the molecules staying in the same place, but the atoms in relation to each other are vibrating. They're wiggling, they're moving around. And rotational motion, so this is a molecule, the motion of a molecule spinning around in place. That's rotational motion. So those are the different types of motion that you can have in molecules. Only the first one is it actually moving from one place to the other. In the last two, they're staying in the same place, but they still can have a motion, and the more motion they have, the more disorderly they are, the greater the entropy. So more complex molecules can have more of each of these motions, so they have greater entropy. There are two principles that determine the direction of a chemical or physical process. The process tends to move from higher to lower energy, and a process increases the entropy of the universe. So let's think about that, okay? Higher to lower energy, things want to fall down, in other words, in physics. And in chemistry, they want to go from a higher energy to a lower energy. And as we said earlier, there's a different type of energy that we're going to talk about here in just a moment. The process also wants to increase the entropy of the universe. Every physical and chemical process that takes place, the overall entropy of the universe increases. So go back to the example of my classroom. You can decrease the entropy and make my classroom more orderly, but the overall order of Hoover High, which would be the rest of Hoover High and my classroom put together, added together, overall the entropy of the school or the universe is going to increase. So ice is a perfect example of understanding this concept. When an ice cube melts to liquid water, think about what happens. Heat enters the ice cube. That's what causes it to melt. So that's a positive delta H. So the ice moves to a higher energy. So think about that. When you melt an ice cube, you have to put heat into it, and that makes the ice cube go to higher energy. But that violates the first rule, that process tends to move from higher to lower energy. So there's something funny there that we're going to have to deal with. But when ice melts, it also increases the entropy, the disorder of the molecules, the water molecules in the ice cube. They become more disorderly. Instead of being locked in fixed orderly positions, they can flow all over the place. So that's an increase in entropy. So that obeys rule 2, that a process increases the entropy of the universe. So you have, when an ice cube melts, one of these rules is being violated and one of them is being obeyed. Now let's look at the opposite process. There are two principles that determine the direction of a chemical or physical process. A process tends to move from higher to lower energy, and a process increases the entropy of the universe. So now let's talk about freezing water into an ice cube. When water freezes into ice, heat leaves the water and brings it to a lower energy state. So that obeys the first rule. When you freeze water into an ice cube, you're pulling heat out, so the ice cube is at a lower energy state than the liquid water. That obeys rule number 1. However, water freezing to ice creates lower entropy. In other words, the molecules of water become more orderly. They become fixed in nice crystalline positions. So water freezing to ice creates lower entropy in the water molecules as they become fixed in an orderly pattern. So that violates rule 2. So whether you're melting water or freezing water, you're obeying one of those two rules and you're violating one of those two rules. So how do we reconcile this relationship between energy going to lower energy and increasing the entropy of the universe? So the preceding two slides show the conflict between the two rules. A process tends to move from higher to lower energy, and a process increases the entropy of the universe. We know that the primary factor that determines whether water freezes to ice or melts into water is what? So what's going to determine whether the water freezes to ice or melts into water? And we know what that is. It is temperature. Higher temperature is going to cause it to melt into water, and lower temperature is going to cause the water to freeze into ice. So the combination of enthalpy delta H and entropy delta S and temperature T leads to a new definition of energy called Gibbs free energy. The formula for Gibbs free energy, also called free energy, is delta G, that's the Gibbs free energy, and delta means the change in, equals the change in enthalpy minus the temperature times the change in entropy. And we're going to spend the next couple of days just studying that equation and how it works. But what I want you to notice at this point is, up until now, up until this lesson, the only type of energy we talked about was heat energy, delta H, enthalpy, going into or out of a chemical reaction. And if chemical systems had to go from higher to lower energy, then all chemical reactions should be exothermic. They should give off energy so that will happen. But we know that they're not. We know some of them are endothermic, that heat can actually go into them and raise them to a higher enthalpy level, a higher heat level. So this is the new kind of energy that will explain how that can happen. So when we say energy, in other words, we're not simply talking about enthalpy anymore. We're now talking about free energy, which includes enthalpy, entropy, the disorder of the system, and the temperature, which relates the two of them. So which determines whether the ice cube is going to melt or whether it's going to freeze. So go back to that ice cube example, really study it till you're comfortable that you see what that conflict is and that we need a way to resolve it. And the way we resolve it is by saying, okay, well, it's the temperature that determines whether the ice cube is going to melt or whether the ice cube is going to freeze. So the units of measure for delta G is joules. It is a form of energy. So it's joules or kilojoules, and that's the normal unit of measure for energy. So there's the formula. So again, it's Gibbs free energy equals change in enthalpy minus the temperature times the change in entropy. So when we say a chemical system wants to move to lower energy, we don't mean just enthalpy anymore. We never did. We mean free energy, delta G, which is the battle between entropy and enthalpy. So free energy is determined by entropy and enthalpy. Entropy means more disorder and higher energy. Enthalpy means less disorder and lower energy. So they're working against each other. And temperature determines which of these factors dominates the battle. So there's enthalpy. There's entropy. And the thing that determines which one is going to win is the temperature in the middle. So key point about free energy, delta G. When delta G is less than 0, the forward reaction, is spontaneous. The reverse reaction is non-spontaneous. Remember when we talked about enthalpy, that the enthalpy, that heat going out, was a negative delta H. It was negative enthalpy. Similarly here, when free energy is going out, it's negative. So that means delta G is less than 0. It's negative. That means free energy is going out. That's a natural, spontaneous process for that to happen. When delta G is greater than 0, that means that free energy would have to be going in. That's not natural. You don't want energy to have to go into a reaction, in this case free energy. The forward reaction is non-spontaneous. That means the reverse reaction is going to be spontaneous. So again, there's the formula. So key point, delta G is negative. The reaction naturally happens, is spontaneous in the forward direction, left to right. Delta G is positive. The reaction is spontaneous in the reverse direction, from right to left. Okay. So delta G is less than 0, it's spontaneous in the forward direction. Delta G is greater than 0, it's spontaneous in the reverse direction. And delta G equals 0, the reaction is in equilibrium. It's going to move neither forward nor reverse. So here's the formula. So we're going to look at some combinations here. We'll go ahead and fill these in, and then we're going to take them one at a time here. Okay, so a process tends to move from higher to lower energy. That means that the delta H naturally wants to go down. You want it to be negative, in other words. You want the heat to come out. And a process increases entropy. That means you want the change in entropy, the delta S, to be positive. So when those two things happen, you see it right there in red. The delta S is positive and the delta H is negative. That means heat is coming out. That's what reactions want to do. That's what physical systems want to do. They want to do both of those things. So when both of those things happen, the delta G is going to be less than 0, the free energy, and that means that the reaction is going to spontaneously move forward from left to right. So the situation in red shows entropy, that's increasing delta S, and heat energy, enthalpy, decreasing delta H. This obeys both rules, so this is a spontaneous reaction. Delta G is less than 0. So there's the same two rules again. So now what you have is the delta S is less than 0. That means it's decreasing. Natural systems don't want to do that. They want entropy to increase in nature of the universe. So that's not natural. Also, delta H is positive. That means heat is going into the reaction. That's also not natural. So those are both entropy and enthalpy being unnatural. Therefore, delta G is greater than 0, and that means the reaction will not spontaneously move forward from left to right. It'll spontaneously move in the opposite direction. So the situation in red shows entropy decreasing, delta S less than 0, and heat energy, enthalpy, increasing, delta H greater than 0. This violates both rules 1 and 2 above, so this is a non-spontaneous process. Delta G is greater than 0. Now the next two situations are kind of ambiguous, meaning they're uncertain. It just depends on what the temperature is in this case. Remember that third variable here is temperature. So there are the two rules again up on the top. So let's read this. The situation in red shows entropy decreasing, delta S less than 0. Well, that's not natural. Entropy wants to increase. So that's violating rule number 2. So this violates rule 2, and heat energy, enthalpy decreasing, delta H is less than 0. That means heat is going out of the reaction. That's what's natural to bring it to a lower energy. So that obeys rule number 1. So you have one of the rules being obeyed and one of the rules being violated. So this goes back to the ice cube example, which you should really read several times and become comfortable, because that's the best way to kind of understand it, because you have a natural understanding for how ice works. High temperature, it's going to melt from ice cube to water. Low temperature, it's going to freeze from water to ice cube. So use that example, keep that example in your head. So if we look at this, so if the entropy, the delta S is decreasing, that means it's going from water to ice cube. The water molecules are becoming more orderly. That will happen at low temperatures. Delta G is less than 0. Also, the heat in that case is negative. That means heat is going out. That's what's happening with the ice cube. The entropy is decreasing because the molecules are becoming more orderly. They're becoming from water to ice, and the heat, the delta H, is negative. That means heat is going out, which is what happens when water freezes to ice. So this is the water freezing to ice example. So this will happen at low temperatures. We know that water will freeze to ice at low temperatures. At high temperatures, it will not naturally happen. You will not naturally have water freeze to ice at high temperatures. So that would be a delta G greater than 0. So this is the situation when water freezes to ice. So this will be spontaneous, delta G less than 0, when the temperature is low. You put the water in the freezer, low temperature, it's going to freeze to ice. And now the fourth situation, same two rules up above. So now you have the delta S is greater than 0. This is the ice cube melting example. So delta S is greater than 0. The disorder is, let me say that again, the disorder is increasing. So the molecules are going from rigid and fixed positions to flowing all over the place. That's greater disorder. That's an ice cube melting. It's also heat going into the ice cube. That's positive delta H. That means heat is going into the ice cube to make it melt. So this is the ice cube melting situation. And when does an ice cube melt naturally? When the temperature is high. That's delta G is less than 0 in the box, in the center box there. Okay, the ice cube will not naturally melt spontaneously at low temperature. That's delta G is greater than 0, so that means that won't happen spontaneously, will not happen spontaneously at low temperature. So let's read this. The situation in red shows entropy increasing, delta S. This obeys rule 2. And heat energy enthalpy increasing, delta H greater than 0, this violates rule 1. So therefore you need temperature to decide which one is going to win. So this is a situation with ice melting to liquid water. So this will be spontaneous, delta G is less than 0 when the temperature is high. So when the temperature is high, entropy will increase and heat will go into the reaction, into the ice cube. Okay, and that takes care of this first lesson on thermodynamics. It deals with a new type of energy called Gibbs free energy. This is the type of energy we're talking about when we say that all chemical systems go to lower energy.